All right, hi, my name is Andrei, and welcome to my talk about the SLUB allocator, or specifically about the internals of the SLUB allocator that would be relevant to Linux kernel exploit developers, and probably also to people who want to just read and understand exploitation write-ups to maybe add some kind of mitigation to the kernel to make it harder to exploit. So I do read quite a lot of write-ups or other resources about the Linux kernel, and what I noticed is that people who write write-ups for exploits, they don't go deep into explaining the internals of the allocator to explain how they shape slab memory to make the exploitation of a slab corruption possible. And then we do have some articles that explain the internals of the SLUB allocator, but the problem is that those don't cover how the SLUB internals are connected to the actual shaping of slab memory in exploits. So what I wanted to do is I wanted to cover the gap that we have and both explain the basic internals of the allocator and then, based on those internals, explain why common strategies of slab shaping work in exploits. There is a bit of a problem with this talk, as technically I need 2 hours to go through all the slides. But what we're going to do is, first of all, I'm going to skip some of the introduction chapters that I have. So instead, well, first of all, probably everyone here, since this is a Linux kernel specific conference, everyone has at least a little bit of an idea about how the kernel dynamic memory management works. So people probably know the difference between the page allocator and the slab allocator, for example. And so I'm going to skip that part. And if you're watching this in a recording, you want to go to the slides and probably check out the slides first for those skip parts. And the second part that I'm going to partially skip is the description of the slab allocator API. So if you know that there is a kmalloc function that allocates memory, kfree function that frees memory, and then you know the difference between like common kmalloc caches versus caches that are created for specific types, then you know everything that I'm going to skip. So yeah. I do want to cover one specific detail about the idea of the slab allocator because we're going to need it when we're going to be discussing specific memory corruption that happen within slab allocator. And I want to explain where the word slab comes from. So the slab allocator, it manages memory in these big chunks called slabs, and these chunks are allocated from page alloc, so from the page allocator. The slab allocator allocates these big slabs and it splits them into smaller object slots. And whenever a user being the kernel, requests a certain amount of memory to be allocated, it gets allocated from one of these object slots in one of the slabs. So technically inside of the kernel you have many different caches. Each cache has its own slabs, so slabs are split into the objects of the same size. And when you call kmalloc, you get a pointer to one of these object slots. So that's like the core idea that we need to know before we proceed. And the next thing I want to mention is that technically the slab allocator does not exist. There are 3 different slab allocators within the kernel, or rather in the upstream kernel right now, there is only SLUB left, everything else was removed. But when you're writing an exploit, maybe you're targeting an older kernel and you might have a different flavor of the allocator. So all of these 3 flavors, SLUB, slab, and SLOB, they follow the same API, but they have different implementation. But for years, the SLUB allocator was the default, so this is what we're going to focus on. All right, let's talk a bit about what kind of memory corruptions we might have with the slab allocator. So the memory corruptions that happen, those are the typical bugs that you might have with any kind of a dynamic memory allocator. You might have out-of-bounds accesses, is-after-free accesses, memory being freed twice, invalid pointers being freed, and stuff like that. Within the talk, we're going to focus on the out-of-bounds use of the free bugs just because there is not enough time to cover everything. But I do have some notes about double freeze at the end, and invalid freeze we're just going not to discuss. Let's look at a few basic scenarios how these memory corruptions can happen. So we do know that we have these slabs which have object slots, and let's assume that within one slot we have a vulnerable object. So throughout this presentation, whenever I'm going to be saying the word vulnerable object, that means that this is a specific allocation that is affected by some kind of vulnerability. And here we assume that our vulnerability is an out-of-bounds access from within the object. So since the object is located within a slab, it might be that the next slot that follows this object on the slab is free. So when we have an out-of-bounds access, this access lands in a free slot, and the SLUB allocator does store some metadata within free slots, so it might be that the access corrupts the metadata or leaks the metadata to user space, for example. And a different scenario, it might be that another object is allocated in the next slot, and in this case, the corruption is happening, so the access lands in an allocated object of a different kind. For use of the free, similar things can happen. So first of all, we can have a use of the free scenario where memory is freed, so memory is allocated, so a specific object is allocated via key malloc, then it's freed via key free, and then it's accessed via a use of the free reference. So we assume that since we have a use of the free bug in the kernel, after the pointer was freed, the kernel still holds on a reference to this pointer, so it can still access it, and this is the use of the free bug by itself. And in this case, we're accessing free slot, so in case nothing else was allocated in the same slot, we access a free slot, the kernel accesses free slot, but it might be that the kernel allocates another object in the same slot, and in this case, the access lands in another object. So these are just typical scenarios that might happen. And a Linux kernel exploit that uses a SLUB bug, what it wants to do, it wants to use the SLUB memory corruption to do either one of two things. So either it wants to attack the metadata that is stored within the free slot. It is tricky with this loop allocator due to mitigation, but it is still possible. Or maybe it wants to corrupt some other object. So you can imagine that if we have another object that contains, for example, a function pointer, and we're able to override that function pointer via out of bounds use of the free, and then make the kernel trigger that function pointer, we might be able to hijack the control flow of the kernel execution and thus escalate privileges, as an example. And this is a much easier approach. So for the most part of the talk, we're going to be discussing the second approach of corrupting a different object. And I'm going to explain why the first approach is tricky with the modern kernels. So for any SLUB memory corruption, you would need three things. First of all, you would need a kernel bug that triggers out of bounds and use of the free. And we're not going to be discussing any specific kernel bugs throughout the talk. We're just going to assume we have one. The second thing that you need some kind of a target object that you want to corrupt or maybe leak. And this is the part that is also out of scope of the discussion. There are many target objects that are commonly used in Linux kernel exploits. So to find out about those, you just there are some lists of objects, there are write-ups, so you can check out those. So this part we will also leave out of scope, and we're going to assume that we chose some kind of an object that we can corrupt, some kind of a kernel allocation with a function pointer, some other pointer that we can overwrite. But the part that we're going to focus on is how to shape SLUB memory to exploit out of bounds and use of the free. So for out of bounds, we'll need to figure out how to put the vulnerable and the target object next to each other. And for use of the free, we'll need to figure out how to put target object into a slot that is referenced by use of the free reference. And this is going to be the focus of the talk. So of course, to understand how to shape SLUB memory for exploiting SLUB bugs, we need to understand the internals of the allocator. So let's start with that. We are going to have some additional constraints on the internals of the allocator. So first of all, I'm going to be targeting the latest long-term kernel 6.6. And the reason is that the SLUB allocator, it evolves and things change. For example, in 6.8, there's already been some changes, and I'm going to reference some of those throughout the slides. This is the first thing. Then the SLUB allocator has a lot of different configuration options, and we're going to assume the most default one. For example, we have the per CPU partial slabs enabled. We have the SLUB debug functionality disabled. It's typically disabled on a production kernel. We're not using the tiny version of the allocator and stuff like that. So some of the things we're also going to leave out of scope, like details about the locking, because we're not really discussing the performance of the allocator. We just want to understand how it works for Linux kernel exploits. And then we're also going to be focusing on a single cache. So we're going to exclude all of the cross-cache corruptions, different kinds of cache interactions like cache merging. So just focus on the basics. All right, let's start with the first thing, is discussing the struct kmem cache. So within the SLUB allocator, each cache has a corresponding structure called kmem cache. And if you check out the definition of the structure, you're going to see that there is quite a lot of different fields within the structure. Some of those might kind of be understandable. So for example, we have the cache name here, the pointer to the name. Each in the kernel, we have different caches like kmalloc caches. So kmalloc caches are going to have kmalloc dash some number as the name. And then, for example, we have the variable that specifies the object size. So this is the size of the objects that are going to be allocated within the slabs for this particular cache. The rest of the fields we're going to discuss one by one, the ones that are relevant to us. So the first field that I want to discuss is a pointer to a kmem cache CPU structure. This is a per CPU pointer, which means there is an instance of this pointer for each CPU core that you have on the system. And as a result, there is an instance for this kmem cache CPU structure for each CPU that we have on the system. And this KMM cache CPU structure holds some data that is tied to a specific CPU within the system, and the reason the SLUB allocator does that is for performance reasons. Usually this is why you use per CPU variables. You might have many CPUs, you want to avoid different CPUs taking locks to access some common, some shared data, so as a result you cache data per CPU. Then we have this other pointer, or an array of pointers to KMM cache node structure. And there is one instance of this structure for each non-uniform memory access node that you have on the system. So this is also done for performance reasons. You can imagine you might have a computer with different memory banks, with different access properties. So within this talk, we're going to assume that we only have a single NUMA node. Discussing multiple nodes is just out of scope. And for the CPU, for now, we're also going to assume that we have only one CPU. The reason is because usually during slab shaping, you want to avoid different kinds of cross-CPU interactions. As a result, you pin your exploit process to a single CPU, and you only interact with the SLUB state for a single CPU. But in some cases, other CPUs might come in and might be relevant, so we're going to discuss those a bit later. So for now, just one NUMA node and one CPU. So each of those structures contain pointers to SLAB structures. So remember, we already discussed what a SLAB is. SLAB is an allocation that holds many objects. And we have some slabs that are per CPU, and then we have some slabs that are per node. So for each CPU, we might have some slabs that are tied to the CPU, and for each node, we might have some slabs that are tied to each node. So here you can notice instead of using a pointer to a slab, here they use a double linked list, but it doesn't matter, this list still contains a list of slabs. Before I explain what is the difference between this slab pointer and partial pointer, and what is the difference between CPU slabs and node slabs, let's study the struct slab in a bit more detail. And this is the next part. So for each slab that we have inside of the Linux kernel memory, we have a corresponding slab structure. And this structure is aliased with the page structure. So page structure is a structure for each physical page that you have on the system, there is a corresponding page structure. Depending on whether this physical page is a normal physical page and maybe it belongs to one of the slabs, the layout of the structure is different. And this is a simplified layout in the case where this page belongs to a slab. And well, the one of the fields is kind of obvious here. For example, there is a pointer to the cache that this slab belongs to. The rest of the fields we're going to discuss. Then remember that each slab, of course, has backing memory. This is the memory that's allocated from PageAlloc, and this is the memory that contains object slots. Some of those slots can be allocated, some of those slots can be free. So depending on how long ago this slab was created, of course, in the SLUB allocator manages the memory in this slot. In this slab, slots get allocated and freed all the time. The size of the allocation that is used for slabs is calculated based on object size, and here throughout the slides I'm going to have links to the specific parts of the SLUB source code that do different kinds of calculations and actions. So if you're studying the slides on your own, you might want to check out those links. And of course, a slab can span up across multiple pages, can be 1 page, 2 page, and bigger slabs. To find out the size of the slab for a specific cache, which might be important when you're writing exploit, you can use the proc slab info file, which shows you different information about the cache. So here, for example, it shows you the object size that is used within each cache, the number of objects that you have per slab, and the number of pages that you have per slab. So for smaller caches, the number of pages that you have per slab is typically just 1 page, but for caches that manage big objects, for example, KMalloc 8K manages objects of 8 kilobytes, and it has 8 pages per slab. Just slabs are bigger, which makes sense. Each slab has a field which is a free list pointer. A free list pointer is a pointer to the first free object within the slab. And first here means this is the first object that is going to be allocated from a specific slab. And as an initial note, there is no pointer to the beginning of the PageAlloc allocation from within the struct slab. And the reason for that is because there is no need for it. Struct slab is essentially struct page. So you can just use there are some kernel macros that allow you to calculate the address that corresponds to a page allocation based on the address of the corresponding page structure. All of the free slots within the slabs are linked via a free list. So we have this free list pointer that points to the first free slot within the slab, and this memory is technically free, which means no kernel user, like the Linux kernel, does not use it, or the Linux kernel external to the SLUB allocator does not use it, which means that the SLUB allocator can store any kind of metadata it wants within the free slot. And the only metadata that the SLUB allocator stores within free slots in the configuration that we assume is a free list pointer to the next free object. So inside of this first free slot, we're going to have a pointer to the next free slot, inside of that free slot, pointer to the next one, and once the free slots within Slab run out, the last pointer is null. And this is how the SLUB allocator links all of the free slots within each slab. So when we are allocating objects from the slab, when the SLUB allocator decides to allocate objects from the slab, it's going to allocate them from the front of the list and also free them to the front of the list. Let's talk about how the free list pointer is stored within the free slot. So it is stored near the middle of the slot, and the way the address of the free list pointer is calculated, essentially they take the address of the object and add the object size divided by 2 and align it to 8 bytes. So essentially this is around the middle, and the reason this is done, it used to be that the free list pointer was stored at the beginning of the object slot, but then if you have a 1 byte memory corruption, like a 1 byte out of bounds bug, you can overwrite one of the bytes of the free list pointer and maybe get a stronger memory corruption based on that. So this is why the free list pointer was moved into the middle of the slot. In addition to that, the free list pointer is hashed. So this is how the hashing happens. The original value of the free list pointer is XORed with the per cache random value, which is generated when the cache is created. And then in addition, it's XORed on something that's based on the address of the slot itself. So unless this was also done to make it hard to fake those free list pointers in Slab exploits. You can imagine that if you can overwrite the memory within the free slot, you might be able to fake the free list pointer if it's just stored there as is. But if it's hashed, you will need to first leak this per cache random value and then leak the address of the slot. So it's still possible, it's just hard. And as a result of these two things, people don't usually target this metadata that's stored within the free slot. So it used to be very common, not anymore. Nowadays, all Slab exploits tend to target the allocation of another object type that is stored within the same slot just because it's easier. So when a new slab is created, all of the slots within the slab are put onto the free list in random order. So it used to be that all of the slots would be put right one after another, and then it would be very easy to shape memory for out of bounds. You just allocate vulnerable, allocate target, and then get placed next to each other. Not the case anymore. Now you don't know the order of the free list slots on a new slab. So as a result, it's very unlikely if you just allocate to objects, then it's very unlikely, even if they belong to the same slab, it's very unlikely that they're going to be placed next to each other. And for full slabs, once all the objects are allocated, the free list pointer within the slab is just null. One last piece of knowledge that we need about the struct slab is that multiple slabs can be linked with each other on a list. And there are two different ways that multiple slabs can be linked. So first, there is a way to use a singly linked list, and this is what is used for per CPU lists. We're going to discuss that a bit later. So there is a pointer to struct slab within the slab structure, which is called next. And then if you have one slab, you can use the next pointer to point to another one, next to another one, and so on until you have the last one where you pointed to null. And in addition, there is the slabs integer field that shows how many slabs we have on the list, including the current one. This is one of the ways that is used, and this is a single linked list. And then they also use the double linked list. This is used for per node slabs. And here we just have a list head structure, so multiple slabs can be linked on a double linked list via this list head. Two different ways multiple slabs can be linked. Okay, as a summary about the slab structure, each slab has its own struct slab. Each slab has its own backing memory allocated from pagealloc. Each slab has one free list, which contains the free slot within the slab, and the free list pointers are stored within the free slots themselves. Faking free list pointers is hard. As a result, we're going to be mostly discussing faking or overwriting other objects. And then multiple slabs can be linked together. Just know that we have two different ways to link them that are used for per CPU versus per node slabs. All right, let's go back to discussing KMM cache structure. This is where we left things off, that we discussed we have this per CPU state, we have this per node state, and for per CPU state we have multiple slabs, for per node state we have multiple slabs. Let's discuss these slabs one by one. So first, per CPU slabs are the slabs that are bound to a specific CPU. And they also, before 6.8, they also used to be called frozen slabs. This is a particular detail of the implementation, so I'm not going to be calling them frozen slabs. Just know that these are the slabs that are bound to a specific CPU, which means that if a specific CPU are going to start allocating objects from this cache, allocations are going to come from these per CPU slabs first. That's the idea. And this is done, for performance reasons. We can cache some slabs per CPU, which means you do not need, the SLUB allocator does not need to take expensive locks to access them. And then, in addition, the SLUB allocator has these per node slabs. And these kind of compared to the per CPU slabs, this is a global list of slabs. So let's consider the case where we have only a single node. So we have multiple CPUs, each with its own set of slabs. And then we have those global slabs, which belong to the only memory node that we have. And note, those slabs are not bound to any CPU yet, but they might become bound, they might be moved into this per CPU list at some point later. But they still belong to the cache and still might contain free slots. I mean, they are still slabs with the objects from the cache. They might contain allocated slots, free slots, and yeah. Let's discuss those two. So when you look at the per CPU slabs that you have, you will see that we have two different pointers. The first pointer is a pointer that's called slab. I call this one active slab, and the other is actually going to be a list of pointers for partial slabs. Let's talk about the active slab first. So one of the per CPU slabs that you have for each CPU is designated as active. And active is the word that I use to describe the slab, but if you check out the SLUB allocator source code, you will see that they call the slab the CPU slab. I think it's a bit confusing when you have the CPU slab and other CPU slabs. So instead, I use the word active slab for the active slab, and the other slabs I'm going to call per CPU partial slabs just to avoid confusion. And this is also what most external write-ups do. If you're reading some exploitation write-ups about the SLUB allocator, it's going to use the keyword active. So active slab has a unique property is that allocations that happen on this CPU from this cache happen from this slab first. And that's the idea. We have one single slab which is used first to serve the allocations. One additional unique property about this slab is it has two different free lists within it. So remember, we already discussed, so each struct slab has a pointer to a free list and it contains free object slots that belong to this slab. But for the per CPU slab, there is actually an additional free list from the KMM cache CPU structure, which also points to the object slots within the active slab. This is the part that's usually missed by most security-related write-ups about SLUB. And it's not particularly useful for exploiting basic memory corruptions, but at the point when you have multiple CPUs working against each other and you have some kind of a racy slab shaping technique, this is the fact that might be relevant. So this is how it works. Let's imagine we have this backing memory for the active slab. We have some free slots within it. And the two free lists, they link slots with the free slots within the slab, but they don't intersect within each other. So we have this lockless per CPU free list that is a field of the KMM cache CPU structure. And lockless, it's in the sense that when the current CPU wants to do some kind of operations with the slab, it doesn't have to take any locks. So it just uses this lockless per CPU free list to free object slots onto the slab or allocate object slots from the slab. And the per active slab free list, it is used in cases when other CPUs want to free objects that belong to the slab. So you can imagine a case when we have an active slab for a specific CPU, but the address of one of these objects on the slab, it's used by another CPU to issue a key free again. So just key frees an address from the slab. So as a result, in this case, the object is not going to be put on the lockless free list, it's going to be put on the per slab free list, and the SLUB allocator will need to take the per slab lock, but this is out of scope of our discussion. So yeah, just know, two different free lists. We have a lockless free list for the current CPU usage, and we have another free list that's used by other CPUs. And the slots on these two free lists, they don't intersect. So these are completely two separate free lists, which means we're going to have two different slots within the slab that end with a null pointer, for example. All right, this was the details about the active slab. Now let's talk about the partial slabs. So partial slabs, this second field that we have within KMM cache CPU structure that's called partial. This is a pointer to a list of partial slabs. So partial here means that these slabs have free slots. So there is at least one free slot within each slab. They can be fully free, but we definitely have at least one free slot. Of course, each of the partial per CPU slabs has its own backing memory, and each of the partial per CPU slabs has only a single free list. So in the active slab, it was more complicated. We had two different free lists. In this case, it's fairly simple, just the per slab free list with the free slots within the slab. And these are the slabs that are going to be used for allocations after the active slab. I will discuss this in more detail in the second part when we're going to be discussing the allocation algorithm. So for now, just know we have the active slab that's used first, the per CPU slabs that are bound to the CPU, but they're not used before the active slab gets full. And the final part is that we have this global list of per node partial slabs. So they're also partial, which means they also have at least one free slot within them each. And they also have backing memory, they also have just one free list, and they're going to be used for allocations after we run out of all the per CPU slabs. But again, more details about this later. There are some limits about how large these lists can be. So first, for the per CPU slabs, for the per CPU partial slabs, there is a maximum number that can be kept on the per CPU list. And this number is described by the CPU partial slabs field of the KMM cache structure. And unfortunately, there is no way to find out this limit from user space. It's just not exposed to user space. Instead, the SLUB allocator exposes a slightly different number, CPU partial, but this CPU partial slabs number is calculated based on CPU partial. So if you know CPU partial number, which you can get from the CSFS file system, then you can calculate the maximum number of slabs that you might have on the per CPU list for a particular cache. And you do need to know this number for certain advanced slab shaping attacks. For example, that the cross-cache attacks, they abuse overflowing this per CPU partial slab list to execute the cross-cache attack. But I'll talk about this a little bit closer to the end. So for the per node list, we also have some kind of a limit, but it's not a hard limit. So instead, for the per CPU partial list, we had the limit of the maximum number of slabs. Here we have the number of slabs that the SLUB allocator tries to keep on the per node list. So this number is exposed. This is called min partial number, and the SLUB allocator tries to keep at least min partial slabs on the per node list always. So even if the slabs get fully free, even there are no allocated object slots, so normally the SLUB allocator would want to free those slabs back to the page allocator because it doesn't need that memory anymore. But for per node slabs, they're an exception. So if we have at least min partial slabs, if we don't have yet min partial slabs on the list, then even if you have empty slabs here on the per node list, the SLUB allocator is just going to keep them around. And here I have a table with the numbers for KML caches. I'm going to skip those because this is just for reference, maybe for those who are writing kernel exploits. So slab of each type can be fully free. We can have a fully free active slab. We can have a fully free slab on a per CPU partial list, and we can have a fully free per node slab. And some of the exploits rely on this behavior that some of the slabs are kept fully free. And for full slabs, they're just not tracked. So the moment the last free object slot within the slab is allocated, at this point the SLUB allocator forgets a reference to the slab and it doesn't keep it on any list. So the moment the SLUB allocator gains a pointer to the slab again is when one of the allocated slots on the slab gets freed. At this point, it just uses vert to slab to calculate the address of the slab structure and then it puts it back onto one of the partial lists. So a bit more detail about the namings. I already mentioned about the active slab, so I use a slightly different naming scheme for naming the slabs. Inside of the kernel code, you will find either the CPU slab or just CPU slab for the active slab. For the per CPU partial slabs, they're named more or less similarly in the source code and my presentation. They're called per CPU partial slabs or just CPU partial slabs. And another difference that we have is here. So these per node partial slabs, I specifically call them per node, but the Linux kernel source code sometimes omits this per node name and instead just says partial slabs. So if you're reading the source code and you see a reference to partial slab, without specifying whether it's per CPU and per node, it's going to be the per node slab. All right, and as a summary, this is the layout that we have. We have KMM cache with one KMM cache CPU for each CPU. The KMM cache CPU has two different types of slab. We have the active slab with two different free lists. Allocation happens from here first. We have a list of per CPU partial slabs. Each has just a single free list. And then we have the per node state with a list of per node slabs that each has backing memory and a single free list. And of course, the full slabs are just not tracked, so they exist somewhere, but the SLUB allocator does not keep them on any list. So this is the summary of the layout that we have within the SLUB. Now, before we talk about our first SLUB shaping exploit, let's talk about how the allocation happen. The allocations happen. I already briefly mentioned that we have active SLUB first, then per CPU slabs, and per node slabs. Let's put it onto the slides. So within the SLUB allocator, we have 5 different tiers of allocation process. Also not an official term, so I just call them tiers. So the first tier is allocating from the lockless free list, second tier from the per active slab free list, then we have per CPU slabs, per node slabs, and finally we can create a new active slab. Let's go through them part by part. So the first step is, let's say we're trying to allocate a specific CPU is trying to allocate an object from a specific cache. The first case is the per CPU partial list, the lockless, is the lockless per CPU free list empty? If the lockless per CPU free list is not empty, then the SLUB allocator just allocates the first object on that free list and we're done. If it happens that this lockless free list is empty, then we go to step 2, we go to tier 2, allocating from the per active slab free list. So remember that within the active slab, we do have 2 different free lists, the lockless free list and the per slab free list. And this tier 2 is when the lockless free list is empty, but the per slab free list is not empty. In this case, what the SLUB allocator is going to do, it's going to move all the objects from the per active slab free list into the lockless free list. For that, it will have to take a lock, of course, and release the lock. And at this point, we can go back to tier 1, which is allocating from the lockless free list. So a bit more complicated for the active slab because we have 2 different free lists, but we allocate from the lockless, try to allocate from the lockless free list first, and then from the free list that requires locking. And if it happens that both of these free lists are empty, or it might happen that we just don't have a pointer to active slab, it depends on the exact branch that is taken within the allocator source code, we just go to tier 3. Tier 3 is allocating from this per CPU partial slab. So we assume we don't have a active slab yet, and we are going to use the per CPU partial slabs. And the way it works is that the SLUB allocator just takes the first slab from the per CPU partial list and then assigns it as the active. Fairly simple. And at this point, we can go to the previous step, allocating from the active slab. So take the first from the per CPU partial list and use that. If we don't have any per CPU partial slabs, we go to tier 4, which is allocating from a per node slab. So in this case, a slightly more complicated thing happens. So first of all, we do take also the first slab on the per node list and assign it as active. But in addition, the SLUB allocator is going to move some of the per node slabs to the per CPU list. So the idea here is that since we run out all of the allocations within the per CPU slabs, most likely this particular CPU is trying to allocate a lot of objects. So it just makes sense to put some slabs onto this per CPU lists so that the CPU can allocate more of them in the foreseeable future. So the first step, designate the first per node slab as active, and the second step is move some of the per node slab to the per CPU list. And at this point, we can just go to allocating from active slab. So this is go to one of the previous steps. And the final case is when we don't have any slabs or any of the lists. In this case, the SLUB allocator just allocates a new active slab. So it goes to pagealloc, asks for some pages, creates a free list for the slab in a random order, assigns it as the active slab, and at this point we can allocate an object from the slab. So 5 tiers: lockless free list, per active slab free list, per CPU partials, per node partials, and creating new slab. All right, this might be a lot of details, so let me explain the core things that we need to know before we can discuss the first exploitation primitive, that exploitation approach that we're going to discuss. So first, we do have many caches, and each cache has many slabs that store objects, some of those object slots. Some of those object slots can be free, some of those can have allocated objects from the previous kernel operation. Then we do have the separation between different types of slabs, and the allocation, they happen from the active slab first. And once the slots in the active slab get run out, we assign the SLUB allocator assigns a different slab as active. And if you think about step 2, so let's say we just start allocating many objects from the same cache on the same CPU. So we're going to fill the active slab, we're going to fill all the per CPU partial slabs and all the per node slabs, and at some point a new slab is going to be created with all slots empty, and it's going to be assigned as the active slab. So these are the 3 takeaways that we need to know. So let's discuss the first very simple case of shaping slab memory for out-of-bounds vulnerability. So this is a simple case in the sense that I assume here that we have 2 different system calls. One system call that allocates a vulnerable object, and another system call that triggers an out-of-bounds access from this object. This is not always the case with out-of-bounds vulnerabilities, but this is the case that we're looking at. So the trigger for the allocation and for the out-of-bounds access, they're separate. And remember that for the attack, we also need other things. We need like a target object. We assume that we have one. And this is the part we're going to discuss now, how to shape slab memory in such a way that the target object follows the vulnerable object in slab memory. So what can we do to achieve this? So for now, I'm just going to explain to you the algorithm that we're going to follow through, and then we're going to discuss why exactly it works. So the first step that most slab exploits do is they want to allocate many objects to get a new active slab. And the reason is they do it is because, well, essentially from the previous kernel operation, you do have the active slab, but it might have some allocations that are unrelated to your exploit. You want to get rid of those, you just want to create some kind of a predictable memory state. So as a result, you just allocate objects, and we're going to be using target objects to fill all the holes in existing slabs. I will discuss why that is a bit later. For now, just let's assume we use our target objects. And we are also assuming that we choose such a target object that can be allocated as many times as we want. Because we have arbitrary choice of target objects, we can do that. So let's discuss how many objects do we need to allocate to fill all the holes and get the active slab. So this is the slab memory that we might have before executing our slab shaping strategy. And these are the slots that we need to fill before a new active slab gets created. So how do we know how many holes we might have in a cache when our exploit starts running? And unfortunately, there is no way to find out the exact number, just because these numbers, they can be found out through the proc slab info file, but this file is just not accessible to unprivileged users. And we do assume that our exploit runs as an unprivileged user. And there is also no upper limit on the number of free slots that we might have. And the reason is that we do have a limit on the number of holes on the active slab. We do have a limit on the number of per CPU slabs, which means we have a number of limits on those free slots. But there is no limit on the number of slabs that can be on the per node list. As a result, there is no limit on the number of free slots or holes, how I call them, on all the slabs. So instead, what people do is they use one of 2 approaches. The first approach is try to estimate how many holes you might have. And the way this works, you just reproduce the environment. So we're assuming we're trying to attack some kind of a target server, let's say, with a certain environment. We reproduce that environment locally. We run the same kernel version. We try to run the same user space workload. We try to give it some uptime, and then see how many holes within the slabs you have on the local system. Because you can debug your local system, you can find it out easily. So I'm going to explain how exactly to get this number on the local system in the next slides. But the problem is that this number is not going to be accurate. Of course, a remote system might have a different number of holes. But this is already good enough as an estimate. It makes sense to take a bit more. Maybe we want to take twice more, 3 times more, 10 times more. But at least this gives you an idea of the order of magnitude of the number of holes that you might have in each specific cache. And there is an alternative which I will leave out of scope. This alternative is relying on timing side channels to figure out whether you allocate, to figure out the moment when you get a new active slab. And the idea is there, you just keep allocating objects and you keep measuring the time the syscall takes to execute to allocate a certain object. And the moment you see that the syscall took a while longer than before, probably this is the moment the SLUB allocator had to go to pagealloc to allocate a new active slab, and this is how you can kind of figure out this through a side channel that you got a new active slab. I do have some links about this approach at the end, but I will leave this out of scope, so let's just discuss the simple approach. Let's assume we're just writing a simple proof of concept exploit, and let's see how we can get an estimate of the number of holes. So within the proc/slab info file, for each cache that you have on the system, you have two numbers. The first number, active objects, this is the number of allocated slots within all slabs that you have for a cache. So each cache can have many slabs, and this is the number of allocated slots. The second number is the total number of all slots, counting both allocated and freed ones. There is a bit of a problem with these two numbers, that for the SLUB allocator, they're not updated all the time, so they're not kept up to date. So if you check here, for example, for CredJar cache, these two numbers match, which is a very unlikely situation that all the holes, all the free slots within all the slabs that we have are filled. This is quite unlikely. So to find out the actual number of holes that you have in a slab, you have to force the SLUB allocator to update those numbers. There are a few ways you can do that, but one of them is you can shrink the cache. So there is a special shrink file which you can write into, and at this point the SLUB allocator will update these numbers. There is a bit of a problem with using specifically this approach, because as a result of shrinking, the SLUB allocator will also free all of the fully free slabs that it has for this cache. So the number of holes is actually going to be different after the shrinking than before the shrinking. But this is still good enough to get some kind of an idea of how many holes you might have. So here, for example, before the shrinking, the numbers were the same. And after the shrinking, we have about 1,000 objects of a difference. So in an exploit, maybe you want to allocate like 2,000, 3,000 objects to fill all the holes that you have in the KML32 cache. Okay, let's assume we filled all the holes, so let's assume we got a new active slab, and it's going to be partially filled with target object just because we kept allocating target objects. So once we got a new active slab, we don't know exactly the moment when we got active slab, because we don't know exactly the moment when we managed to plug all the holes. So the assumption is that we do have some target objects on active slab. Now we're going to use our syscall that allocates one vulnerable object. And of course, because the allocation happened from the active slab, the object is going to be allocated from the active slab 2. And it's going to be placed somewhere in the slab, we don't know where exactly. Step number 3 is we're going to fill this active slab with target objects. So we do know that the maximum number of objects per slab for a particular cache is a certain number. This is the opt per slab number. And we do know that we already have at least one object within the active slab, which is the vulnerable object. So we just allocate opt per slab -1 target objects on top. And the first few of them are going to be placed in the active slab. So the active slab is going to be filled. And then, of course, maybe a new active slab is going to be created and some of the target objects will spill there. But we don't care about that. The thing that we care about is that we fill our new, old active slab with the target objects. And at this point, if we triggered out of bound access, it just happens that it lands in one of the target objects. So our slab shaping approach allowed us to create a new slab which has one vulnerable object, and all of the other object slots are taken by target objects. And as a result, it's very probable that the object that follows the vulnerable object is going to be the target object. And this is what we wanted to achieve. So let's discuss what is going to happen if we skip some of the steps. First, what's going to happen if we skip this step 1 when we allocate target object to plug the holes and get a new fresh active slab. So this could be the original state. We could have some original active slab before we started our slab shaping, and it has some allocated objects from the previous kernel operation. And it can happen that once we allocate a vulnerable object, it just gets placed before one of those previous kernel objects, and we fail to corrupt target because we end up corrupting some other kernel memory, which is bad. This is why we do this first step of filling the holes and creating a new active slab that only contains target objects. Then the question is, why do we specifically use target objects to fill the holes? What if we use some other type of object? Let's call them plug objects. So let's say we use these plug objects to get a new active slab, to fill all the holes and make the SLUB allocator get a new active slab. Some of those plug objects will end up on this new active slab. And at this point, if we allocate vulnerable object and it happens to be placed before this plug object, then we fail to overwrite target object, we overwrite our plug object instead. So this is why we use target object for plugs. The reason is because we have some objects allocated during step 1, we have some objects, then vulnerable object, and we have some target objects allocated during step 3. And the vulnerable object, it can be placed before an object from step 1 or before an object from step 3. So in both steps, we want to use target objects. There are some things that can go wrong. For example, it can happen that the vulnerable object is placed last on the slab. So a slab has a certain limit. If vulnerable object ends up last on the slab, then we fail to override target. So as a result, slab shaping, there is no way to make slab shaping work in 100% of cases. Well, this particular problem can be resolved. It requires the page allocator level shaping, so you can just shape page allocator memory in such a way that this slab with the vulnerable object is followed by another slab that filled with target objects. In this case, you can resolve this and get 100% of success chance with regard to this specific issue. But we'll leave it out of scope. So just know that there can be some problems. Another problem that might happen, so let's assume we have multiple CPUs and we start executing our slab shaping strategy. So it could happen that our exploit process gets migrated to a different CPU in between, like during the slab shaping execution. So this is a problem because once it's migrated to a different CPU, it starts using the active slab of that other CPU. And our slab shaping strategy fails because it relies on the fact that we use a specific active slab and the active slab does not change throughout slab shaping. Luckily for this particular problem, there is an easy way to solve that, is we can pin the exploit process to a specific CPU, and this can be done by an unprivileged user. So just call the shared set affinity syscall, and this problem is resolved. However, there is still a different problem, which is called preemption. So preemption is different from migration. Preemption, and when the task that's being executed on a certain CPU gets preempted by another task to be executed on the same CPU. And this is also a problem for us because if our exploit process gets preempted in the middle of slab shaping, some other process that starts running on the same CPU, it might start using the same cache, so it might start using the same active slab within the cache, and it might allocate free objects from that active slab. And this is a problem. And for dealing with preemption, unfortunately, there is no single perfect approach. There is just some ways you can kind of deal with that to get your slab shaping strategy work in most of the cases. So here I have some of the ideas. For example, it makes sense to minimize the time you spend on slab shaping, just because if you spend a lot of time, if you add some debug printfs in the middle of your slab shaping, probably not something that you want to do because you increase the chance that your exploit process gets preempted. And this is a problem. If you have a choice, you can use a less noisy cache, which means you can try, let's say you have a vulnerability, and for that vulnerability, you can choose object from which cache you're going to attack. Maybe KMalloc 128 or KMalloc 256. And then you can debug the kernel and see which of these two caches is used more frequently and use the one that's used less frequently to avoid. So even your exploit process gets preempted, to avoid the case that these other tasks start allocating from the same cache. Then there are some other things like getting a fresh scheduler time slice before executing the slab shaping, or checking whether you got preempted by reading this proc/self status file, or maybe timing side channels. But there is no one perfect solution. So slab shaping does not always work. You can make it work for certain. Like you can make the success chance of slab shaping to be like 99.9% for certain types of exploits, but it's never going to be 100%. Okay, let's discuss a slightly more complicated case. And this is the case when we have a combined allocation and out of bounds trigger. So in the previous case, we had a separate syscall which allocated vulnerable object and a separate one that triggered out of bounds. And in this case, we have one that both allocates an object and then immediately triggers out of bounds from the object. And with this second case, we cannot separate steps 2 and 3. So remember that in the previous approach, we had step 2 allocating vulnerable object, then step 3 fill the active slab with target objects, and only then we triggered out of bounds. With this combined approach, we cannot separate those will happen in the same step. So this is what we're going to do instead. I'm going to discuss two different approaches to this problem within the presentation. For now, this is going to be the allocation only approach. So here we're going to be relying on the allocation primitive only. There is a different approach that you can use, but it relies on knowing how the frame works within the slope allocator. So we're going to move on to that later. So the allocation only approach works like that. First, we do the same thing. We create a new active slab with target object. So at this point, we don't touch vulnerable object yet, so you can just allocate many targets to get a new active slab. And at this point, we're just directly going to use our alloc and out of bounds trigger to both allocate an object and trigger out of bounds without filling the active slab. And let's see what can happen. The first thing that can happen is that the slot that follows our vulnerable object is going to be a free slot. And let's say we have an out of bounds write primitive, and we're really worried about corrupting some critical kernel memory because this is going to crash the kernel. And the thing is that if our out of bounds write primitive does not write too much bytes out of bounds, we are going to be fine because the only metadata that we have within a free slot is a free list pointer, but it starts somewhere in the middle of the object slot. So we can safely override the first few bytes, so depending on the size of the slot, maybe even more, and it's not going to cause any memory corruption. Of course, we're not going to corrupt the target objects, we're not going to override the target objects too, because it's just not here. But the important thing is that we're not going to crash the kernel, which means we can retry this slab shaping. Okay, we can retry this slab shaping approach and just do it all over again. So you can free all the objects and refill the holes and try it again. And at some point, hopefully, this is what we're going to get. It just will happen that our target object gets placed into the slot that follows the vulnerable object. So this happens. This target object is allocated from step 1 when we're filling the holes. And it just so happens that our exploit works. So this is fairly interesting because it used to be that free list pointer was stored in the beginning of the slot. And then when it was stored in the beginning of the slot, this type of thing wouldn't work. But now that the free list pointer is moved into the middle of the slot, it actually helps us with this particular exploitation approach, which is fairly interesting. So maybe, I don't know if it's a good idea to move it back into the beginning, because, well, some kind of a poison thing might work too. Yeah, but this is fairly interesting that it works now. All right, so far we covered the allocation process, we covered 2 different approaches to shape memory for out of bounds, and now let's talk about the freeing process so we can discuss use of the free too. And for the freeing process is fairly more complicated than the allocation process, so I'm going to split it in 2 parts. We definitely have enough time to go through the first part, and for the second part, well, we'll see. All right, so within the freeing process, we're going to look at a few different cases. So it depends which object is getting freed. And the first case for the first part we're going to look at is when the object that gets freed belongs to the active slab of the current CPU. So let's assume this is the object that gets freed, and it's freed by CPU A. And this is one of the slots of the active slab for the CPU number A. So we have Chemium Cache CPU for CPU A, we have the active slab, we have the backing memory, and this is the object that gets freed. And in this case, the freeing process works very simple. The object gets put on the lock list per CPU free list. So this is the free list that's used to allocate objects from this active slab on this CPU. And this is also the free list that's used to free the object. So it used to be here, now it's on the lock list free list. Very simple. And the only exploitation relevant outcome of this approach that is going to matter to us. Let's assume the following scenario. Let's assume we allocate one object via kmalloc, we free it. We allocate object of the same size again, we free it. We allocate another object of the same size again, we free it, allocate, and so on. All of these pointers are going to be pointing to the same object slot. Because when you allocate an object, it gets allocated from the active slab. When you free it, it gets put on a lockless active slab free list. When you allocate it, it gets allocated from the lockless free list. When you free it, it puts on a lockless free list, and so on. So all of these are the same object. Pointer 1 equals pointer 2 equals pointer 3. And this is very, very useful for us for exploiting use of the free box. So let's discuss the first case of exploiting use of the free. Let's assume we also have a simple use of the free vulnerability. So at this point we have 3 ioctls. We have 1 to allocate vulnerable object, 1 to free it, and 1 to access it. And this ioctl use of the free can be used after the object was freed. So I assume we can call ioctl alloc, ioctl free, and ioctl use of the free. And we want to shape slab memory to exploit this type of a memory corruption, so we want to override some kind of target object. Let's see how this works. So first we're going to allocate a vulnerable object. For this approach, you don't even need to plug holes, assuming you can directly allocate your vulnerable object via a yoctal, via some kind of syscall. No need to plug holes, you just allocate one object, it gets placed on the active slab because objects always get allocated from the active slab. Then you use ioctal free to free it back to the active slab, and of course it gets put onto the lockless per CPU free list. And we assume we still have some kind of a reference to this slot from within our vulnerable subsystem, just because we found the vulnerability and we have a use of the free reference. At this point, if we allocate target object, just one target object, it's going to be put onto the same slot just because the slot belongs to the lockless free list of the active slab. And here we have a target object and we have a use of the free reference that points to the target object. So at this point, if we trigger use of the free, we succeeded, we overwrite our target object with the use of the free access. Very simple. So unfortunately, this is not always how use of the free vulnerabilities work. In this case, we have a very nice vulnerability in the sense that we can allocate object and nothing else gets allocated. We can free it and nothing else gets freed and trigger use of the free. Sometimes it happens like that, but in a lot of cases it's way more complicated. It may be than when you allocate a vulnerable object, 10 more object, 100 more object get allocated in the same cache. And in this case, reclaiming that freed object slot is going to be more complicated. And this is going to be the part of the case 2. So before we move on to case 2, let's discuss the rest of the freeing process. So far we only covered one part, if the object belongs to the active slab of the current CPU. Let's discuss the second case. The object that's being freed belongs to a slab that is not active slab for the current CPU, and this slab is not full. So we're going to have case number 2, when we have a slab that's not full, and case number 3, which is going to discuss when the slab is full. In those two cases, the SLUB allocator behaves differently. So let's say we have this other slab, and this can be maybe active slab of another CPU, or it may be one of the per CPU partial slabs for one of the CPUs, or maybe one of the per node partial slabs for one of the nodes. The first step in this case is also simple. The slab gets put onto the per slab free list. So for this other slab, regardless of what kind of slab it is, we always have this per slab free list, and the object slot that was just freed, it gets put first onto the free list. And then an additional thing that happens, and this is only applicable to per node slabs. So if it was a per node slab and the slab becomes fully free after this last object was freed from it, it might be that the slab is going to be freed directly to page allocator immediately. This happens when we already have enough slabs on the per node partial list. Remember, we had two limits. We had a limit on the per CPU partial slabs, which is a hard limit from above, and we have a kind of a limit on the per node list. And the SLUB allocator tries to maintain a certain number of per node slabs, but if it already has enough per node slabs and this slab gets free, then all of the object slots are free, then the SLUB allocator will just free it back to page allocator because it does not need that memory anymore, and this slab gets freed. So this does not apply to per CPU partial slabs, and it does not apply to active slabs. So only for per node slabs, it can be freed immediately during this case number 2 when we free a slot from a non-full slab. All right. Now, a particular subcase of this case that we just discussed, it can happen that we have this object that belongs to a active slab of CPU number A, but the freeing happens by CPU number B, so by a different CPU. This is what's going to happen here is exactly what we just discussed. So the object is going to be put on the per slab free list for the active slab for that CPU number A. And the second step, this is not a per node slab, so it cannot be freed, so the second step is not applicable. Just as an example, that this works the same way for per CPU, for active slabs of other CPUs. All right, and let's discuss the last case, which is the most complicated one. If the object belongs to a full slab. So let's say we have some kind of full slab, we have a reference to it, and this is the object that gets freed. So the first step is the same. The object gets put on the per slab free list for the active slab. But at this point, the slab itself becomes a partial slab. So the SLUB allocator has to put it onto one of the lists. And the question is how exactly it happens. So what the slope allocator is going to do is going to try to put this slab on the per CPU partial list. The only problem is that we have a certain limit on the number of slabs that we might have on the per CPU partial list. And depending on whether this limit is exceeded or not, different things happen. So in the simple case, when the number of slabs that we have on the per CPU partial list is not going to be exceeded, so we have less than the limit. In this case, our new slab that was just full, that contains the object that's being freed, it's just going to be put first onto the per CPU partial list, while in the rest slabs, the slabs that we had before will follow it. So nothing will happen with regards to those. So this is the simpler case. The more complicated case is when we already have a lot of slabs, so we already reached the limit on the number of per CPU partial slabs. In this case, the slope allocator will want to free up this list of per CPU partial slabs. And this is how it's going to do it. So it's going to go through that per CPU partial list slab by slab, and then it's going to move those slabs to the per node list and to the end of the per node list. It's not particularly important for us for the exploitation strategies that we discussed, but it does move it to the end of the list. And then while it's moving those per CPU slabs into the per node list, it might free some of those back to the page allocator. So if we have a per CPU slab that is fully empty at this point, and we already have enough per node slabs, then at this point the per CPU slab will go back to the page allocator. And this is the particular behavior that's abused for cross-cache attacks. And we will leave this out of scope, but I'm going to have a reference to an article that describes how cross-cache works, and this is the behavior they rely on to free some of these per CPU partial slabs back to the page allocator to execute the cross-cache attack. So yeah, once the slabs are moved to the per node list, or maybe some of them get freed, at this point we have space on the per CPU partial list, and the slab to which the freed object belongs, it just gets put first on the partial list. So this case number 3 is the most complicated case that I discussed throughout the slides. So this is the case when we have a full slab and we free an object from the full slab. First object gets onto the free list, then the slope allocator tries to move it to per CPU list. If the per CPU list has space, it just gets put first on the per CPU list, the slab itself gets put. If the per CPU free list is already at the limit, the slope allocator is going to free it up by moving the slabs to the per node list, and then it's going to put the new slab first onto the list. This might be quite a few details to understand immediately, so it might be that those who want to figure out how this works will have to go through the slides once more. But here I'll give you the most important outcomes that we need to discuss the next strategies. So first, if we have an object that belongs to a per CPU partial slab and that object gets freed, the object itself, it goes on to the slab free list. So let me show a picture for this case. So if we have an object, maybe I don't have a picture here. Anyway, if we have an object in a partial slab, the object just gets moved to the free list of that slab and nothing else happens. If we have an object in a full slab, then the object does get put onto the free list for the slab, and the slab becomes the first per CPU partial slab. So if you go back here, you can see that in both cases, regardless of whether the per CPU partial list overflows or not, the new full slab always ends up first on the per CPU partial list. So in the case the partial list does not overflow, the slab that has a slot that was just freed, it ends up first on the per CPU partial list. In the case where the slab, the per CPU partial list did overflow, the slab which contains the object that was just freed, it still ends up first and the only slab on the per CPU partial list. So this is the second outcome that we need. The third one is for cross-cache attacks, so I'm going to skip it. All right, so let's discuss a more complicated case of shaping memory for use of the free attack. So this is what we discussed before. This was the simple case when we're interacting with a lockless per CPU free list. We allocate vulnerable object, free vulnerable object. At this point, it's lost on the lockless per CPU free list. We can just allocate one target, and it's going to be placed again onto the same spot, and we're going to reclaim it. But in practice, it might happen that your use of the free vulnerability is different. And for example, it might happen that the use of the free reference you have to one of the slots, it's not the last slot on the per CPU lockless free list. It might be one of the slots on one of the CPU partial slabs, or maybe one of the slots on even on a per node slab. It really depends on the nature of the vulnerability that you have. And one specific case that I'm going to briefly discuss in when we're trying to upgrade out of bounds to use after free, it's going to be in a few slides. In the next few slides. And in this case, let's say what we're going to get is we're going to get a use after free reference to the first slot on the first per CPU partial slab. So the question is, if use after free reference points to here, but we still have an active slab, how would we reclaim that memory? And we're going to discuss that too. But first, let me explain what I meant by upgrading out of bounds to use after free. It's also one of the tricks that you can use with SLUB exploits, and let's see how that works. So remember how we shaped memory for simple out of bounds when we allocated many target objects to get new active SLUB, allocated vulnerable object, filled the active SLUB with target objects, and then triggered out of bounds to override target. So it might be that you don't want to use that out of bounds bug that you have to directly get control of the kernel, so to exploit the kernel only with that particular primitive. Because out of bounds primitives, sometimes they're powerful, but sometimes they can be fairly weak. For example, if you have a single byte out of bounds, it's very hard to corrupt something meaningful inside of the kernel to directly get code execution. So often what people do is they want to upgrade this out of bounds primitive to a stronger primitive, and typically people upgrade it to use after free primitive just because use after free is usually way stronger than out of bounds in terms of things you can do with the exploit. And let's say we're using such a target object here that contains like a ref counter or some kind of pointer that might get freed or something else at the very beginning of the allocation. Let's say the ref count. So in this case, if we use our out of bounds bug to override the ref count of the object, it might be that we will be able to turn this into use after free. For example, we can decrease the ref count, and in this case, the object is going to be freed, the target object can be freed before the kernel gets rid of all the references to it. And this is the case that we're going to discuss. So let's say we shaped memory for that simple out of bound case, and let's say we chose such a target object that contains ref counter at the beginning. And let's assume we allocated target object in such a way that the ref counter, the initial ref counter that it has number 2. So we have two different references from different parts of the kernel to this target object. So let's use our out of bounds primitive to override this reference counter from 2 to 1, just as an example. So we assume that the has the initial ref count of 2, and well, technically, we do know that the SLUB becomes full after shaping. So when we executed our out-of-bounds shaping strategy for the simple out-of-bounds bug, we fully filled this SLUB with target objects, which means it's one of the full SLUBs right now, and it's not tracked by the SLUB allocator. So let's corrupt our ref counter, increment it from 2 to 1, and then for each target object that we allocated from user space, I assume we have some kind of references to those objects, like a file descriptor or something else, and we're going to close those file descriptors once for each of the target objects to decrement the reference counter from each target object from 2 to 1, at least for those that we initially allocated. But since we corrupted the ref counter for this object that got placed after the vulnerable object, its ref counter was 1. So when we close the file descriptor once, the object got freed, and at this point we have a dangling reference to the slot. And the thing is that this slot is going to be this slab to which the dangling reference belongs. It's going to be one of the per CPU slabs. So remember that during the slab shaping for simple out of bounds, we fully filled the slab, which means the slab became a full slab. And by closing the file descriptor, we do now have a free slot within the slab, but it's not the active slab. So it got placed on the per CPU partial list, and let's assume it got placed first there. So the question is now, how would we reclaim that slot on the per CPU partial list in the case when we didn't have the slot on the active slab? So the solution here is very simple. We use slab spraying, and the idea is also very simple. Just allocate more objects. So remember, when we are trying to exploit use after free on the active slab, we just needed to allocate one object because we knew that the slot is lost on the lockless free list. But in this case, the slot is buried somewhere deep within the slab allocator free list. So we just need to fill all the slots before it. And this is when we use slab spraying. So the idea itself is similar to the case when we just allocate many objects to plug holes. But I prefer the term spraying when you have some kind of a slot that you're trying to override, trying to target. like plugging holes, you have many holes, and with this case, you have a particular slot. But the idea is the same. The only question is how many objects do you need to spray, and this depends where exactly your free slot, to which slab exactly it belongs on the lists. So let's assume this case. Let's assume we managed to upgrade our out of bounds to is after free, and let's assume we got the first slot on the per CPU partial slab. So how can we fill it? So first we have this new active slab. And the thing is that on this active slab, we might have up to opt per slab free slots. Well, technically opt per slab -1, but let's assume the case that opt per slab slots for active slab. So first we have to fill those slots. So what we do, we start allocating target objects, and this can be different target object. We used one type of target object for out of bounds. Maybe right now, when we have use after free reference, we want to use a different type of target object. But it can be the same one if you want. And so first we have to fill the slots on the active slab, and to do that, we allocate opt per slab target objects. And once we allocated opt per slab target objects, it might already happen that one of those objects is going to reclaim our slot on the per CPU slab if the active slab was not fully free. So if we only had a few free slots, then once we allocate, like in this case, we had 4 free slots, we allocated 4 objects, and object number 5 is going to be placed here already because this is the next slab that's going to be used. But in the worst case, we're going to have 8 free slots within the active slab. So the first opt per slab allocation are going to plug those slots, and the next one is going to be placed inside of the per CPU partial slab. So here, the only difference here is that the free slot with the use after free reference, it's buried deep into the list of slabs, so we have to plug all the holes before it, before we can reach it. Otherwise, the idea is similar, just allocate objects to reclaim. Okay, I'm 5 minutes out of my time, but I hope it's okay. I spent 10 more minutes and then we should be done. And let's discuss another approach, how we can shape slab memory for an out of bounds, for the out of bounds case where we have combined allocation and out of bounds trigger. So we already discussed how to do it by just kind of like hoping that the slot that follows the vulnerable object is going to be the target object. And in this case, let's see, maybe we can do something else. Now that we know how freeing process works, maybe we can do something better and we can do it without retrying. So I want to explain to you the making holes approach. I don't think this is official name, it's just how I call it. And the idea here is that we're going to create a slab full of target objects, make one hole there, and put our vulnerable object inside of the hole. So this is how it works, how it's supposed to work. First of all, we again allocate many target objects to plug all the holes and get a new active slab partially filled with target objects. Then we allocate even more target objects, opt per slab on top, to make this slab become full. So now we have a slab that's filled with target objects. Now we free one of those target objects. So I assume while we're allocating our target objects, to each target object we have a reference from user space. We don't know the order of the target objects within each slab, but we know that if we go opt per slab allocations back in time, then that allocation will definitely belong to a different slab that we're currently working with. So we just go opt per slab allocations back, free one object, and then we get a slab with a hole. And then the idea here is that we want to reclaim that hole with the vulnerable object, and that immediately going to trigger out of bounds. And this is going to, we're not going to need to retry, because in this case we only have one hole within the slab, everything else is target object. So if our vulnerable object gets placed within the hole, then we will get a target object in the next slot, and then our slab shaping strategy succeeds. The only problem is that placing this vulnerable object within the hole, within this slab that used to be full, is tricky. And the thing is that, again, here we have the case. Once we fill the object, with the slab with the target object, it became a full slab. And once we make a hole in the slab, it's going to be placed on the per CPU partial list. So if once we get that, we allocate just one vulnerable object, which is immediately going to trigger out of bounds. If we just allocate one vulnerable object, it's not going to be placed into the hole. We already have a different active slab, so it's going to be put in a different active slab. And we could try to allocate multiple vulnerable objects to plug all those holes in the active slab, and eventually this hole is will be used. But the problem is that each time we allocate vulnerable object, it triggers out of bounds. So we don't want to do that, because that will likely end up corrupting some kernel memory. So instead, we need to somehow improve this approach to allow us to make this particular slab to be active again, and only then allocate one vulnerable object. And this is how we're going to do it. So let's start over the whole shaping strategy thing, and let's discuss how to do it to deal with this case. So the first step is going to be the same. We're going to allocate many target objects to plug all the holes and get a new active slab partially filled with target objects. And the number of holes in the slab we don't know, but it will be up to per slab holes. The next step is that we're going to reserve many full slabs. So for this approach, instead of just creating one full slab with target objects and making a hole in one slab, we're going to create many of them. And the number of full slabs we're going to create is going to be one bigger than the number of potential holes we might have in the active slab. So we reserve obfs per one full slabs, and to do that we just keep allocating targets. If you allocate obfs per slab multiplied by the number of full slabs you want to get target objects, at this point you will get this many full slabs. The next step would be for each of these full slabs, now we have, like we know that we have obfs per slab plus 1, in this case it's going to be 9 full slabs. What we're going to do, we're going to start going through our list of references in user space to our target objects through the list of file descriptors. So let's assume each time we open a file, a target object gets allocated. So we go through our list of open files, and for each, when we go backwards, and for each obfs per slab file descriptors, we close one of them. And this will result in this case, so for each of our full slabs, in each of them we're going to make a single hole. And of course, when we're going to be making the first hole that's going to be made, the slab is going to become the first per CPU slab. That we're going to make another hole, it's going to be also become a per CPU partial slab. But the problem is that for all the caches that you have, the obfs per slab plus 1 is going to be bigger than the maximum number of slabs that you might have on the per CPU partial lists. As a result, this per CPU partial list at some point will overflow, and the slabs will spill to the per node slabs. So after you're done dealing with these holes, you're going to have some of the slabs with the hole on the per CPU list, and some of them are going to be on a per node list. And again, the total number of slabs that we have here in this particular case, we're going to have 9 slabs with the hole, and the maximum number of holes you might have on the active slab in this particular case is 8 for the particular picture that I have. So now let's imagine we start allocating objects. So first, objects are going to be allocated from the active slab. Then an object is going to be allocated from the first per CPU slab, at which point this hole is going to be filled and the per CPU slab is going to become full slab and is going to be gone. Then the next per CPU slab is going to be used. Then at some point we're going to run out of these per CPU slabs and we're going to go to the per node list. And that list also have slabs with the holes, so those holes are going to be used next. So let's say the maximum number of holes that we might have in the active slab is obfs per slab. Let's first allocate our obfs per slab target objects. So as a result, what we're going to have, in this case I use plug objects, but it doesn't matter, target objects work too. For this case I just made it plug objects, so on the picture you can see it better which objects got allocated at this step. So let's allocate obfs per slab plug objects. First, those objects were allocated from the active slab. So we had an active slab with 4 free slots, those slots got filled. Then we had some partial slabs, some slabs with a hole on the per CPU list, and those slabs got full. Then maybe we went out to the per node list and some of those slabs got full. But the thing is that at the very end, even in the worst case, we're still going to have at least one slab with a hole, just because we created one full slab more than the total maximum number of holes in the active slab. And at this point, we allocate vulnerable object and it gets placed within the hole that we have, and we do end up overwriting the target just because we shape memory in such a way that we fill that potentially last slab with the hole at this step with a vulnerable object. So a bit more complicated in this case, we did need to know all the behavior within the slope allocator, we did need to know about all the lists, how to make holes, which is the order of the allocation, and this is the approach that you can use for this combined out-of-bounds approach. So the upside of this approach is that it works even in cases when your out-of-bounds bug might corrupt the free list pointer, if it's like a bigger out-of-bounds, so you end up overwriting free list pointer, which you usually don't want. So this works. This approach also has some disadvantages, and the biggest problem is that it's not very reliable. So first of all, allocating that many full slabs takes time, and it's very likely that you're going to get preempted, especially for caches with very large ops per slab number. And the second thing is that in this approach, we start interacting with the per node list, and this is a global list. And the thing is that other CPUs might interact with that list too, which adds additional source of unreliability. So in certain cases, you might have to do it, but typically, SLUB exploits, they tend to avoid dealing with the per node list just because other CPUs deal with that too, and you don't want that. You don't want any kind of source of unreliability. All right, some notes about double free. So just briefly, typically double free, what people do with the double free, they turn it to use after free. So you free slot once, replace it with some kind of object, free it again. At this point, you have a reference to the object and you trigger use after free. I'm already out of time, so I'm not gonna go through that in a lot of detail. So a few final notes. First of all, SLUB is complicated. Whatever I showed here is just a model. It's a simplification. If you want to understand how it actually works, you have to go read the source code and the two particular starting point I linked here, the starting point for allocation, the starting point for freeing, and hopefully the information on the slides is enough to get you a head start, and then you read the code and it should be understandable. Then some additional links about the SLUB allocator. The first one is about internals of the SLUB allocator, and it covers what I covered here, except the slab shaping strategies, and also adds some additional details about SLUB debug and about Kasan, so I do recommend checking this one out. Then once you're done with figuring out how this basic slab shaping strategies work, you might want to explore cross-cache, and this is the best starting point to explore cross-cache. Sorry, the last article about a good starting point to explore cross-cache. And the part that I didn't cover was about cache merging, the accounting, the different caches, the hardened user copy, and this is the article that you want to check out for that. Finally, some links about those timing side channels that I mentioned. These are 3 different papers. The most modern one is SLUB Stick, but the older one, you might still want to read them for getting some inspiration, or maybe getting some ideas about how to use timing side channels. And yeah, at this, thank you. If you have any questions, I don't know if you have time for questions. What is the format here? There is no moderator, so I guess we have time for questions, but thank you. Sorry? Okay, perfect. Then yeah, thank you. This is the end of my presentation. If you have any questions, please ask them. Yeah.
I have 2 questions actually.
Okay.
So the first one, in the slab structure in the kernel cache, you have 2 int fields. You have a CPU partial and you have a CPU partial slab.
Yes.
I'm not sure that I understood correctly the difference between the 2. Can you please explain it again?
Yes. So CPU partial slabs is the actual limit on the number of slabs that you might have on the list. So this is the actual limit. The other number is, I believe this is the limit on the number of object slots that they might want to have on this partial list, but they don't count. I mean, I think this is just some legacy reason. The original code was not limiting the size of the list itself, but the number of free slots that they had on this list. But at some point, they decided it's more efficient to limit the number of actual slabs, so they reworked the code. But since this number was still exposed to user space, they wanted to keep it exposed to user space, the original number of the potential number of, potential limit on the number of free slots on these slabs. So they kept it.
Okay, so the first one is about object. The second one is about the number in the element in the list, right?
Yes, correct.
And the second one, you say that when the slab is full, is actually put outside of the kernel cache, outside of the structure. But then where it is stored, because you still need to get the information about it, because if you free something from the full slab, then you will put it back into the kernel cache.
Yes. So for the slab, we have the slab structure and the backing memory. So the slab structure, it stays there. It's one of the page structures. So there is an array of page structures, maybe multiple arrays, and this is just an array, and it's always there. And if a particular page structure is a slab, it's just going to have a different layout. So that always stays there. The backing memory, it's allocated from page alloc, and yeah, if we have a free slot here, there is going to be a link to this free slot. once we have no free slots, there is no link from the slab structure to this memory anymore. But the thing is that there is, so you might want to explore this vert to slab macro. The way this array of page structures is allocated inside of the kernel, there is basically one-to-one mapping from the array of page structures to the physical pages, to the addresses of physical pages that you have. As a result, if you know the index within the array of page structures, you know the address of the physical memory. If you know the address of the physical memory, you know the index within the array. It's slightly more complicated because you can have multiple arrays, but the idea is still the same. If you know the address, you can get the address of such slab accordingly. So the code, what it's going to do once you get a pointer to a certain object, it's just going to use that vert to slab macro to get the address of the corresponding struct page. And that macro just calculates the address within the array of page structures based on the address of the page.
Thank you.
Yeah.
Thank you for the great presentation. Just out of curiosity, recent editions, I think it's in 6.11 kernel, we do have the option for allocating or for using different camel caches, basically one per subsystem, for example.
Yeah.
I believe there's also something similar provided by GR Security that works very similar, let's say. From my understanding, I mean, I understand how it protects against these kind of attacks, but it doesn't completely solve the problem, correct? It basically reduces the attack vector to that subsystem, meaning that the attacker will have to be able to control both sides, allocating and freeing from the same subsystems, but the end effect is fatal.
So, yeah, I mean, I think you're referring to the patch set by case. That's essentially, this is not something I discussed during the presentation, because in the presentation we focused on a specific cache. So we assume we have a cache, we assume we have ways to allocate objects from the cache, and we didn't discuss cache interactions. But the thing is that within the kernel, yes, you might have those common k-malloc caches, for example, and different parts of the kernel, if they use the same cache, the objects allocated from the different parts of the kernel, are going to end up in the same cache. And that patch set prevents that type of thing of happening. So like the latest patch set that's still being discussed is one based on the code location inside of the kernel code, even though the code, like the call that you have to the allocation functions, it's still k-malloc, it's supposed to be using k-malloc cache, but at this point, for each code location, you have your basically standalone cache, a separate cache, and it just uses allocations from that cache. But yeah, that does not prevent the problem. Well, it prevents a part of the problem. It makes it way harder to choose, for example, target objects for exploitation. So in the case that I discussed here, let's assume we can have vulnerable object coming from one kernel subsystem and target object can be coming from completely different kernel subsystem. This is what happens typically right now without this patch that case has. But once you have that patch, if you have a certain vulnerable object, that means you will have to base your exploit on corrupting the same type of an object. So you're going to have to use vulnerable object or object of the same type as your target object. It still does not solve the problem fully, because you can still corrupt objects of the same type, and it might give you some kind of a better primitive that you will use for some other things. But it definitely makes it harder.
Thanks.
Yeah. Well, I mean, I don't know. So this thing that case has, the last one, the one we just discussed, it's fairly exciting. I don't know if distributions will actually enable it, because as far as I understand, it results in big fragmentation. But we'll see. This is one of the things that is cool. Another thing is the SLUB virtual thing by Jan Horn and some other people from Google. So this is the thing that prevents cross-cache attacks. This is something I didn't talk about, but essentially, what they do is they try to limit the, basically for each cache, so imagine you have a cache, and you have slabs that are allocated for that cache. And those slabs contain objects of a certain type. And what they want to do, they want to avoid cases when you have a reference, when you have some kind of a cross-slab interaction. For example, if a cross-cache attacks, the way it works is let's say you have a use after tree reference to a object slot within the slab. They take the whole slab, they free everything else in there, they free it back to page alloc, and they allocate it as a slab for a different cache. And as a result, you might have a reference, use after tree reference to certain memory, which was originally a slab for a cache type A, and at the end you have a reference to a cache type B, which allows you to do a lot of fun things. And Slab Virtual prevents that. This is one of the things that makes it fairly interesting. It's also not bulletproof because at the moment you're doing cross-cache, you can do a cross-allocator, how I call it, cross-allocator attack. So instead of corrupting once you freed memory back to page alloc, instead of allocating this memory as a memory of another cache, you can just allocate it as page tables. It's just a simple page allocation, and you can corrupt page tables, which is a very flexible approach. So something else needs to be done about that, but for cross-cache attacks specifically, Slab Virtual is quite fun. And otherwise, yeah, we have MT, at least we have it, kind of have it on ARM. Well, we do have it on ARM. The question is, we don't yet have it in the Android kernel. There is a debug implementation that's not enabled by default, but MT will certainly make it very interesting for a lot of cases for this type of memory corruptions primitive. So MT is memory tagging for those who don't know. This is another type of a mitigation. Essentially, the MT allows tagging different slots of memory with different tags and different pointers with different tags. And then the memory can only be accessed through a particular pointer if the tag on the memory matches the tag on the pointer. So if you manage to somehow make the pointer point to a different part of memory, the tags are not going to match, and you're not going to be able to dereference the pointer. All right, thank you.